classroom support on Monday who fixed the computer. It did some things. It was always messed up for most of the semester. But today we're back to where we were last week. And so now the only button that works on this monitor is the one to select the pen and none of the others. So that'll be an interesting experience. But I think we'll make it work. You got your exam 3 scores? I haven't seen them. I'm not involved with that, but how did it go? Good for some of you at least. Oh, all right. That's encouraging. Okay, so what we started talking about Monday was reactions of enolate anions and enamines, and we've made it through a bunch of content. Let me see. We started with some, general ways of enolate anions reacting. We've looked at the acidity of alpha hydrogens that are abstracted to make enolate anions. We've looked at the aldol reaction, potentially the most important reaction of enolate anions, and some of its variants. We've looked at the mechanism, we've looked at the crossed aldol reaction using 2 different components, ideally one lacking alpha hydrogens, and we've looked at the Henry reaction, a variant of the aldol reaction that instead of an enolate anion uses a nitronate anion, the conjugate base of a nitroalkane, and we've then used this in a synthesis, and then we ran out of time. Let's see, right over here. There we are. We ran out of time right over here, and I've introduced this reagent, sodium cyanoborohydride, that I think you were not familiar with. And so I just want to talk very briefly about how this reagent works. So hopefully you do recall, I'm going to abbreviate everything here except for the amino group as, let's say, R prime. You hopefully do recall that aldehydes and ketones react with primary amines. How am I going to do this? React with primary amines to form imines. I think I got it. I'll go like this. Aldehydes and ketones react with primary amines to form imines. Those have carbon-nitrogen double bonds. But in the process of the imine forming, there is a key intermediate, an iminium ion, right? And it is this iminium ion that is reduced by sodium cyanoborohydride that will act as a hydride ion donor, reducing the iminium ion to the amine. And sodium cyanoborohydride being less reactive than sodium borohydride, we know that sodium borohydride, NaBH4, would of course reduce a ketone. Sodium cyanoborohydride doesn't do that, but it does selectively reduce the iminium ion to an amine. So if your goal is to take an aldehyde or ketone and a primary or even secondary amine to make an amine, to make a carbon-nitrogen single bond, just combine your amine and your carbonyl compound, aldehyde or ketone, and add sodium cyanoborohydride, and you can make that amine in one step. All right. Now back to those aldol reactions. We're almost done with them, but one more thing we want to look at is the intramolecular version of this reaction, where the 2 ends that are reacting with each other are part of the same molecule. And so intramolecular reactions, if we're making carbon-carbon bonds, for example, form ring structures. So specifically 5 and 6 membered rings are favorable here, and that's what we use this reaction for. So we're starting from a diketone on the left. This is hexane 2,5-dione, an example of a 1,4 diketone, meaning if we count from one carbonyl carbon to the other, first one is carbon number 1, the second one is number 4. Now, each one of our two ketones has two alpha positions, but these two primary alpha positions are, of course, equivalent, right? They're related by symmetry. So there's that one type of primary alpha position, and then we have a secondary alpha position. Those two are also equivalent. So fundamentally, there are two different enolate anions that can form, and we'll take a look at those. If we abstract an alpha hydrogen from the primary alpha position of either ketone, here's the enolate anion that would be generated. Now for option number 2, if we instead abstract an alpha hydrogen from the more substituted from the secondary alpha position, this is the enolate anion that would be generated. So there are two. And one is more stable than the other, but both of them form to different extents and different amounts. The equilibrium here with the, comparatively weak base that we're using, sodium hydroxide is not a weak base, but to make an enolate anion quantitatively, that won't do. So we'll really have an equilibrium favoring the side of the diketone with a little bit of this enolate and a little bit of that enolate floating around, and that reaction going back and forth. But it's not about which one of these forms to a greater extent, but about which one of these can form a reasonable product in an intramolecular reaction. And we have to remember these are carbon nucleophiles, and the nucleophilic carbons in both of them are highlighted. The enolate acting as a carbon nucleophile in each case would attack the other carbonyl carbon, the remaining aldehyde or ketone. So looking at the first enolate anion, and considering the ring size that would form when the carbon that I labeled C1, the nucleophilic carbon in the enolate, were to attack C5, the carbonyl carbon, a 5-membered ring would, of course, form. In the second enolate anion, we have the secondary alpha position. That would be the nucleophilic site, the nucleophilic carbon atom. If you think about your alternate resonance form, this is the carbon that would have the negative formal charge. So this carbon would attack this ketone over here, and a 3-membered ring would form. We would connect the carbons numbered 1 and 3. So which of these two scenarios is the more likely one? What ring size will we form? We'll form a 5-membered ring, of course, because a 3-membered ring, these exist, but they don't readily form in these intramolecular reactions because they're very strained. And so that 3-membered ring, because of the high ring strain it would experience, will not form here, when we can much more easily form the 5-membered ring, which will have a little bit of ring strain, but nowhere near as much. Okay, so what will that look like? The enolate on the left side, the primary alpha position being deprotonated, will act as a carbon nucleophile, will attack the second ketone's carbonyl group, push the CO pi bond electrons onto oxygen to make your tetrahedral intermediate. What will the resulting intermediate look like? And we'll actually go all the way to the aldol addition product here. But, in terms of the thought process, let's perhaps just start with the ring size, and then we'll work our way there. We know that we're going to make a 5-membered ring. And carbon number 1 was part of the enolate anion. This is where we originally deprotonated. If you follow your curved arrows at C2, we are reforming our carbonyl group. Attacking C5, we're breaking the CO pi bond. We're going to be left with the CO single bond, negative charge on oxygen, and C5 is also bonded to a methyl group. Now that negatively charged oxygen bonded to C5 will subsequently be protonated, and so that'll give a hydroxyl group. There's our aldol addition product. Maybe I'll highlight the electrophilic site in our enolate anion as well, so that we can see which two atoms specifically made that bond. And so now finally, if we apply heat, we know that dehydration will occur between the carbons here that are labeled C1 and C2. That dehydration will make a double bond. And we know where that double bond forms because the product will be an alpha beta unsaturated carbonyl compound, will be a conjugated system. So there's the product of this particular intramolecular aldol condensation. There's the product of that aldol condensation. All right, let's do another one. The next one is going to be a little more complex. This is an example from the Brown text where I think they go only over the correct solution without kind of eliminating all the other possibilities first, which is what we're going to do. So clearly, this starting material contains two unique ketones. Each one has two unique alpha positions. So there are four possible enolate anions that can form, and we'll take a look at all of them, and then we'll evaluate which one should actually be the one undergoing the reaction. So at the lower left side, the bottom of the six-membered ring, let's label this alpha position A and draw the enolate anion that would form if that alpha position were to be deprotonated. So here's what that enolate anion would look like. This is our major resonance contributor. But we have to keep in mind always that enolate anions are carbon nucleophiles. This is the nucleophilic carbon atom. Okay, so there's option 1. Now for option 2, we'll take the other side of that same carbonyl, this tertiary carbon atom. Let's label that B and abstract an alpha hydrogen there and take a look at the resulting enolate anion. There's our second candidate. And again, always remember these are carbon nucleophiles. So I'm highlighting the nucleophilic carbon again. Now the exocyclic ketone, we'll start with the alpha position to its left. We'll abstract a proton and draw the resulting enolate anion. So there's candidate C, again a carbon nucleophile, and that leaves us with one more alpha position. The exocyclic ketones less substituted alpha position, so we'll abstract a proton there as well. And there's going to be our fourth and final enolate anion, candidate D. And again, that is a carbon nucleophile. So now, how would all of these react in an intramolecular aldol reaction? Bless you. The carbon nucleophile in each case, like I said, these buttons aren't working right. The carbon nucleophile, the enolate as a carbon nucleophile in each case, would attack the other carbonyl group, the other carbonyl carbon in the same molecule if an intramolecular reaction were to proceed. Can you predict what ring size we would form from enolate A? Counting from the nucleophilic carbon, the one that I highlighted, to the carbon that you're attacking. I'm not leaving a lot of room for me to add any notes. But what you should find is that there should be a six-membered ring forming. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That should be a six-membered ring. But you can perhaps also, I don't know to what extent you can visualize it, but you might see that you're going to have some kind of a bridge bicyclic structure. And we'll get back to that in a moment, I think. But let's just say for now that the ring size would be, the new ring that we make would technically be a 6-membered ring. And again, we'll get back to that in a moment. We'll look at this in a little bit more detail, probably on MolView. All right, candidate B. Here's what the intramolecular addition of the enolate to the ketone would look like. What ring size would form in this intramolecular reaction? Count carbon atoms from the one that's highlighted to the ketone you're attacking. 4-membered ring. This is where you're starting. This is your electron donor, 1, 2, 3, 4. These 2 carbons would be connected. You'd be making a 4-membered ring. And so we know 4-membered rings are also fairly strained. They're not that much less strained compared to a 3-membered ring. And so it's probably not happening. The 4-membered ring is not going to form. Now, what about enolate C? I think you can see it coming. We'll have the same problem. The highlighted carbon atom, this is the atom that will donate your electrons, will attack this ketone. So that'll make a 1, 2, 3, 4-membered ring once again. And we know that ring size is fairly strained. Ring strain in the neighborhood of 25 kilocalories per mole. A 5-membered ring only has about 6. I almost said 6, 7, because it's literally like 6.5 or so for cyclopentane. I try to avoid it at all costs, but sometimes it just happens in context, and then I'm like, I did not just say that. I don't even know if that's a thing in your age group, but it's kind of, you know, better safe than sorry. All right, so another 4-membered ring, that's no good. That leaves us with one final contender here, enolate D. Again, the highlighted carbon atom, that's the carbon nucleophile. From here, we attack the ketones, carbonyl carbon, push the CO pi electrons onto the O. That would be our nucleophilic addition. And what ring size would form here? Another 6-membered ring, so that looks good. So now the question is, what's the better option, A or D? And you may already see what's better, but I think we'll look at letter A in a second. What was I trying to get at here? There was something I was trying to say, but I can't remember. So maybe it wasn't important. I'm just going to pull up MolView real quick so that we can take a closer look at, it's giving me some trouble. So we can take a closer look at A. And I will go ahead and share that on Zoom for a second, and in the classroom we can see it on the left and on the right. So what I will do is this. I will start with our starting material. Okay, starting material. It's not pretty and it doesn't have to be. So this is where we start. Okay. And in contender A, we take this carbon atom, right? This is where the enolate formed, and we attack there. And so we're going to get rid of this double bond. We're going to go down to a single bond. That's better. So from here, attack there. It's not pretty, but the atom connectivity is right. And so what we're seeing on the right side is the 3D model. And I'm going to try to rotate this a bit. The 3D model of the aldol addition product. I'm trying to kind of line this up with our drawing on the left, which doesn't include any stereochemistry, but it's like, what did MolView do here? Did it give us a mirror image or something? That works. Okay, so here's the original 6-membered ring with our original ketone. Does that work? I literally cannot make sense of it. No, yeah, that's right. All right, so there's the original ketone. This is where the enolate formed. This is the chain bonded to the original ring, and this carbon attacked there, if that makes sense. So why are we looking at this? Because our goal is not to look at aldol addition products, but rather, press the wrong button again, but rather to look at aldol condensation products. So I'm going to add some heat here just to make that clear. And does this aldol addition product, this model, look like that would give a clean dehydration? In a dehydration, we would make the alpha beta unsaturated ketone. So there's our ketone, there's our alpha carbon, there's our beta carbon. The double bond would form here, and the double bond would involve this bridgehead atom. Now, right now, this bridgehead atom is sp3 hybridized, so roughly tetrahedral. After dehydration, that atom would be sp2 hybridized. Geometry should be trigonal planar. Well, is that possible? Can this atom be trigonal planar? Can it be flat? It can't. These bridgehead atoms don't form double bonds because of, let's say, geometric constraints. It cannot, this atom cannot adopt a planar geometry. And so effectively, even if this aldol addition product forms from the first enolate, and it probably does, it would not dehydrate. It cannot dehydrate, and only the final part of the dehydration of this, of this mechanism is irreversible. So if the dehydration doesn't happen, well then there's still an equilibrium. So we have our enolate D. Let's see. There's my pen. I'm just going to add a note to enolate A, and I'm going to write that the addition product cannot dehydrate, and we've just seen why. The addition product formed from enolate A, which may very well form, there's an equilibrium there. That addition product cannot dehydrate, it cannot eliminate water to form the final product. And remember, only that last step of the mechanism, that elimination of hydroxide in the dehydration, is irreversible. Everything else before that is reversible. So far, enolate D is looking the best. And so following this through to the end, we can go ahead and predict our aldol addition product. We are forming a new 6-membered ring. Atom 1, 2, 3, 4, 5, 6. Atom 1 attacks atom 6, like so. Now some parts are missing. Actually, I wish these buttons were working. All right. So our carbonyl group is at C2. C1 attacks C6, where we break the CO pi bond, push those electrons onto oxygen. That'll create a negative charge, and following protonation, we'll end up with a hydroxyl group. So this is the aldol addition product that would form. Now the two bridgehead atoms here, I don't know if we can call them bridgehead atoms, but the atoms shared by our two rings are shared by only two rings. There's no bridged bicyclic structure. So those can easily be planar. So dehydration should not be a problem here. How many stereoisomers of this aldol addition product could form? I mean, there are 2 chiral centers. How many options are there? 4? There are 4 stereoisomers of this aldol addition product that can form. But if we take this through to the end, apply heat, dehydration occurs, a double bond will form between the alpha and beta positions, the alpha position of the ketone that is next to that beta position bearing the hydroxyl group. This is where water is eliminated. This is where our double bond forms. So what does the product look like? after dehydration, this is the alpha beta unsaturated ketone that should form. Now, how many chiral centers does that molecule have? How many chiral centers do you see? One? There's just one. And so what I want you to do is include stereochemistry whenever you draw a product that has stereochemistry that has chiral centers. For these bridgehead atoms, it's most convenient to just add the hydrogen and show it pointing towards you or away from you. So there's one product stereoisomer. And in the second one, in the enantiomer, we'll just have the same hydrogen point away from us. And speaking of, things I expect you to do, thinking about your last exam of the semester, I'm working on putting together practice exams so that you kind of know what to expect in terms of questions. I have, I think, 2 of them just about ready, and I'll make a 3rd one. And I'll post those probably a week before your I don't want to say final exam, it's not a final, but before your 4th exam, so that, you have what you need to prepare. Okay, so there's our final product. This took a minute. Here we are. So we made a 6-membered ring, and we didn't have any trouble dehydrating, which we would have had in the addition product formed from the enolate that we labeled A. All right. Now we've kind of walked through this reaction going forward, largely from the starting materials to the products. But how do we recognize that a given molecule has to be made, or at least can be made, using an aldol reaction? And how do we determine what the starting materials should look like? What does a retrosynthetic analysis look like? Well, if we're talking aldol condensation, what kind of molecule is made, what kind of perhaps functional group or kind of structural feature is made in an aldol condensation? An aldol condensation makes an alpha beta unsaturated carbonyl compound, generally an alpha beta unsaturated aldehyde or ketone. And well, the first target molecule here is an alpha beta unsaturated aldehyde. There is an aldehyde, there's a carbon-carbon double bond, and the 2 are conjugated. So that's your indicator, that's your pointer that an aldol reaction, an aldol condensation is one of your options. It's not the only one. If we're looking into how we could make this double bond, what's another option to make this double bond? Like, how do we make double bonds? Not as in we have a single bond, but we want to make it into a double bond, but there is no bond, and we want to connect 2 carbons that in the end should share a double bond or make a double bond. What's the reaction that makes a carbon-carbon double bond? The Wittig reaction? You have heard that before. All right, so that's another option that we're not going for here, but it's an option. Okay. All right, so we have this alpha beta unsaturated aldehyde. Typically, it is this carbon-carbon double bond that is made in the aldol reaction in the aldol condensation. But you want to better be safe than sorry, because there are some examples where a double bond might form in an unexpected place, and there will always be a good reason for that, but it can be hard to pick up on that working backwards. So what forms first is the aldol addition product, which is a beta hydroxycarbonyl, a beta hydroxy aldehyde in this case. So the beta carbon that's part of your double bond in the alpha beta unsaturated aldehyde, that is the one bearing the hydroxyl group in your aldol addition product. Your aldol addition product that forms before dehydration is your alpha, or not alpha, just beta hydroxyaldehyde. So there's that. And actually from here, it might be a little bit easier even to visualize what your starting material would have looked like. Which bond are you forming? You're forming a bond between the alpha position of one aldehyde or ketone and the carbonyl carbon of another aldehyde or ketone. One aldehyde or ketone forms an enolate. That'll be your nucleophile that forms at the alpha position. and your other aldehyde or ketone will be attacked by said enolate at its carbonyl carbon. I don't know why this keeps happening. Okay, one of my highlights disappeared. This one. Okay, so this alpha position is where the enolate was formed previously from an aldehyde, and this was the other carbonyl carbon. Why is my highlight disappearing? This was the other carbonyl position. This is where that other carbonyl carbon was located. Stay there. Okay. So what did the parent carbonyl compounds look like? The electrophile was butanal. Its carbonyl carbon is the electrophilic site. And what was the nucleophile? The nucleophile was the enolate anion formed from also butanal. The enolate forms at the alpha position right here. The enolate of butanal forms and attacks the carbonyl carbon of also butanal in this aldol self-condensation, giving first this addition product, and then dehydration gives the aldol condensation product. So if you had to predict a product going from starting materials to products for this, very simple self-condensation, all you would have to do literally is to connect the alpha position of one aldehyde to the carbonyl carbon of the other. Just make a double bond between these two atoms, and you have your product. So for simple reactions with very simple reactants, it's fairly straightforward. But as soon as you kind of run into reactants where at least one of them perhaps has multiple carbonyl groups, that's when you kind of want to take it step by step, because things can happen along the way that you didn't expect. Okay, we do have a second example, an alpha beta unsaturated ketone. An alpha beta unsaturated ketone, and we've seen this on Monday actually, but either way, working backwards, this aldol condensation product forms from the aldol addition product, which is this beta hydroxy ketone. And how does the beta hydroxy ketone form? The enolate anion formed at the alpha position of a ketone in this case would attack the carbonyl carbon of another aldehyde or ketone, an aldehyde in this case. So this is the bond that would in fact be formed in this aldol reaction. Wrong color. There we go. All right, so the electrophile would be, take everything to the left of the cut that I indicated here, and your CO single bond was originally a double bond, so your electrophile is benzaldehyde. And then everything to the right of that cut, that's simply acetone. I'm clicking all the wrong things. All right, so acetone's enolate would add to benzaldehyde, make a new carbon-carbon bond, break the CO pi bond. That's how you end up with your single bond. Throw on a proton, you have your hydroxyl group, eliminate water, final product forms. Now, how many of you have started tackling some problems regarding aldol reactions? More than 0, which is good, but the rest of you should get caught up. Try to stay on top of things, whatever reaction or topic we're covering in class. Before I see you again, you should ideally, review your notes, study from those notes, try to make sense of everything, memorize the parts that you have to, make sense of the parts that you can, and then start testing yourself. Apply what you learned to problems so that you can see, did you get it? Can you solve those problems? And if you can't, what's the hang up? Fix it before, we're going into this any deeper. All right, so that's the aldol reaction for now. The electrophile here was always an aldehyde or ketone, so whenever we formed a tetrahedral intermediate, there was no leaving group. There was no leaving group to be eliminated, and that is about to change in this next reaction, the so-called Claisen condensation. This one's not a made-up name. This one is named by a scientist, or not by a scientist, after a scientist. We've looked at the self-condensation of aldehydes and ketones previously. Now we're looking at the self-condensation of esters. Starting with the simplest textbook example, the self-condensation of ethyl acetate. So I've drawn two equivalents of ethyl acetate here for a reason. To kind of give you a broad overview here of what is happening. One ester will have to form an enolate anion, of course, at its alpha position. And we'll walk through the mechanism shortly, but still. One ester will form an enolate anion. Its alpha position is going to be deprotonated. And the other ester will serve as the electrophile and will basically undergo the usual addition-elimination mechanism and therefore lose its leaving group. And so the product that is generated here is a beta keto ester. This particular product is acetoacetic ester, but it's an example of a beta keto ester where we've made this bond right here. For this Claisen condensation to work well, your product should at least have one acidic alpha hydrogen. This product should have at least one acidic alpha hydrogen, so one alpha hydrogen shared by both carbonyl groups, and we will learn why that is once we look at the mechanism. But without that acidic alpha hydrogen, you probably won't obtain the desired product. When you look at the base used in this reaction, we started from an ethyl ester, ethyl acetate, and the base used here was sodium ethoxide, so it turns out this base matches the ester. For an ethyl ester, you're going to want to use an ethoxide base, sodium, potassium, whatever you have on hand, but your base should match your ester typically, unless you use something super bulky like LDA, or if you use sodium hydride, that's not going to cause any problem. Can you see a problem with using an ethyl ester and maybe sodium methoxide? Could these two react? Methoxide could act as a base, creating enolate anions, certainly, but what if it attacks? What if it reacts as a nucleophile? Can you see a problem there? Now you have two leaving groups, one methoxy group, one ethoxy group. Which one will be eliminated is anyone's guess, probably going to be some statistical distribution, and now you have a mixture of ethyl esters and methyl esters. They're no longer the same. You'll have a hard time separating them. So you want to make sure that your base matches your ester so that if your base does attack your ester, it doesn't cause any change as to in terms of what ester you actually have, methyl, ethyl, something else. What you also don't want to use is hydroxide. In terms of basicity, it's of course similar to methoxide and ethoxide, but what does hydroxide do to an ester? It hydrolyzes the ester, doesn't it? It hydrolyzes an ester to initially form a carboxylic acid, which is then immediately deprotonated to form a carboxylate. So in the case of ethyl acetate, saponification would occur, hydrolysis would occur to give sodium acetate and ethanol. And sodium acetate will not form an enolate anion under these conditions. Our reaction won't work. Instead of our Claisen condensation, we'll see an ester saponification. And again, that's not what we're looking to do. So choose a base that matches your ester. And on the worksheet, you'll see scenarios where I did go with a different base, but the bases that I chose, first of all, they're literature examples, so I know they worked. And secondly, maybe the base was particularly bulky. There was a reason why it could be used, because it wasn't able to attack the ester itself and mess with that. All right, now for the mechanism. really we've drawn a general mechanism, but we probably haven't talked, about intricate details of this mechanism. So given that we're going to see the formation of enolate anions from an ester, let's take into account the pKa of those alpha hydrogens. I think I'll go with a different color here. Here is one of the alpha hydrogens of our ester ethyl acetate. The base is ethoxide, sodium ethoxide. The ethoxide anion is, of course, the one to be abstracting the alpha hydrogen, and this will generate the ester enolate. And you can see I'm pushing electrons into the ester's carbonyl group because the goal here is to generate the major resonance contributor. So deprotonation of the ester forms its enolate. That's a carbon nucleophile. That'll be the nucleophile in this Claisen condensation. Protonation of ethoxide gives ethanol, which is the solvent, so that's just going right in there, not a problem. What's the position of equilibrium here? Left or right? What's the pKa? We have the pKa of the acid. What's the pKa of the conjugate acid? 16, so 25 and 16. Which acid is weaker, the acid or the conjugate acid? The acid is weaker. Higher pKa means less acidic. So which side does the equilibrium lie to? The left side, the side of the weaker acid. What's the equilibrium constant? 10 to the negative 9-ish? It sounds about right. So what is the ratio of products to reactants? 1 to a billion? So there's very little of that. There are very few enolate anions that form an equilibrium here, but we don't need many. We just need a couple, and then they can react further, and more of them form Le Chatelier's principle. Things keep going. All right, we've just made our nucleophile. What's next? That nucleophile needs an electrophile. What is the electrophile? It's the ester. Not the enolate, but just the simple ester. The ester is the electrophile. I'm going to highlight the nucleophilic and electrophilic sites, but it's anyone's guess if those highlights will stay where I put them. The enolate anion, that's our carbon nucleophile, and the ester on the right, that's the electrophile. The enolate acting as a carbon nucleophile will attack the ester's carbonyl carbon. We break the CO pi bond, pushing pi bonds up and out of our way to create a tetrahedral intermediate. So we're adding something to an acid derivative. We're adding the enolate anion to the ester. What does the resulting tetrahedral intermediate look like? Let's see. Yeah, that'll work. There's our tetrahedral intermediate that forms once the ester's enolate attacks another ester molecule. The ester molecule being added to, being attacked, forms a tetrahedral intermediate. And this tetrahedral intermediate contains a leaving group. Regular acid derivative chemistry here. And given that a leaving group is present, our tetrahedral intermediate collapses and eliminates that leaving group. And so that's the second part of the usual addition-elimination mechanism. We know this is the type of mechanism that acid derivatives undergo when they react with nucleophiles. Elimination of our leaving group ethoxide actually gives our product and said ethoxide anion our leaving group. It's not very pretty. I think I'll redraw some part of this. Okay, that's good enough. So there's the product of the reaction. Make a nucleophile addition elimination. It looks like we're kind of done. Now we've made this beta ketoester, and we have alpha hydrogens here that are shared by two carbonyl groups. So we know that these are particularly acidic. And you should know roughly how acidic they are. Their pKa is about 11. So we've just created this product that has acidic hydrogens, alpha hydrogens, and we've eliminated a leaving group, which equals the base that we're using. Is there, like, does the reaction end here, or does something happen to that product? Remember, these alpha hydrogens are fairly acidic. Your leaving group that was just eliminated is a base. Will there be an acid-base reaction? Well, we could at least try and find out and see if the answer is yes. So let's have our base abstract one of these alpha hydrogens and form an enolate. I'll draw the enolate of the ketone rather than the ester, just because the ketone will stabilize the negative charge better than the ester. All right, push those electrons into the ketone, form the enolate, the conjugate base of your product, and protonation of this ethoxide anion gives ethanol. So the question is, does this proton transfer, does this acid-base reaction happen? If you think about this as an acid-base equilibrium, does that equilibrium lie to the reactant side or does it lie to the product side? Again, look at your pKa's. You have the pKa of the acid. You know the pKa of the conjugate acid. Which acid is weaker? The conjugate acid, the pKa is 16, it's higher. The equilibrium lies to the side of the weaker acid, which is the product side. So this proton transfer is happening, and these proton transfers are very fast. The equilibrium constant is 10 to the power of 5, so 100,000 to 1 ratio of products to reactants. That's happening. Now, we don't necessarily want this to happen, but it is happening. And this step is crucial because it kind of traps our product in the form of its enolate. And because the equilibrium constant is so high, it's basically irreversible at this point. And all the steps leading up to this one are reversible. So there's really just one big equilibrium between your starting materials, the ester and base, and your product, which tends to not favor the product. But as soon as the product forms, because there's at least one acidic alpha hydrogen, we've mentioned that, the product is trapped as the enolate. It can't go back now. It's stuck here. And so this is the end of step one, the reaction with the base. We have the enolate of our product that was made. And this is when we add our acidic workup, aqueous HCl or aqueous, I don't know, ammonium chloride, anything just mildly acidic, to neutralize our reaction mixture that'll destroy any excess base, making all of those previous reactions, the reverse reaction, impossible. And so that is how we're going to be able to generate the final product of that reaction, how we're going to be able to isolate our beta ketoester product. And I'll sketch how that forms, of course. Under acidic aqueous conditions, we'll have a solution of hydronium ions in water, and one of the ions will protonate the enolate to again generate the product. So if I were to ask you to draw the mechanism of this reaction, you can't stop here. The next two steps kind of look redundant, like why would you deprotonate just to protonate again? But it's not like we are doing this because we want to, because we feel this is a good idea. It's that this is happening. We can't stop this from happening. So we need to show that, right? This deprotonation is inevitable, which is why that acidic workup in the end is required. Yep. I'm pressing a button, waiting for it to do something, but it's not happening. Okay, yeah, if we go back to the previous slide, you can see in the reagents, we're first reacting with our base. And then once that part is complete, once we're certain that all of our starting materials has been consumed, then we add our mild acidic workup, dilute aqueous HCl, or again, like ammonium chloride solution or something like that. So yeah, that's going to be part of the reagents, and you have to include that so that I know that you know it's necessary. All right. Now we can have starting materials that contain two ester functional groups, and we can use these in an intramolecular Claisen condensation, which has its own name. It's the so-called Dieckmann condensation. So Dieckmann condensations are intramolecular Claisen condensations, and those intramolecular reactions, again, are used to make 5- and 6-membered rings. We have one starting material shown here, 7 carbons, so that is diethyl heptane dioate, a 1,7 diester that we use to make this 6-membered ring, the cyclic beta keto ester product. And we'll illustrate some of this, perhaps not the whole thing. I don't know why I'm drawing an oxygen. I was intending to draw an alpha hydrogen. We have 2 ethyl esters in our starting material, which means we should use ethoxide as a base that matches the ester, so that we don't saponify our ester, so that we don't change one ester to another. And so the first step, as before, is the deprotonation of an ester to form its enolate. And that is an equilibrium that does lie very strongly to the reactant side. But again, that's fine, as long as there are some enolate anions that can kind of go forward. If we arrive at our product, eventually that product gets trapped as its enolate, making the reverse pathway effectively impossible. So there's the enolate that forms from one of the esters. We've formed our nucleophile, and that'll attack the carbonyl carbon of the second ester, which will then, of course, serve as the electrophile. That'll look like this. Attack, form a tetrahedral intermediate. So we're adding a nucleophile, we're adding the enolate to an ester. Is anyone wondering why my curved arrows sometimes look like this? I know not all of you have seen these before. I've seen this in a textbook I reviewed, and I thought it made sense. So what I'm doing is this. I'm showing you the movement of this pair of pi bond electrons, but before I move them anywhere, I show you kind of which atom I assign them to. So this pi bond is used by this carbon atom to attack there. Does that make sense? It's more intuitive in terms of what's the atom connectivity in the next intermediate. You don't have to use the arrows the way I do. You can just draw your curved arrow from this bond to that atom. But I draw them this way because, again, I find it more intuitive. It explains a little bit more of the process. It shows that this is the atom that uses those electrons. Otherwise, I might think it's this one, but it's not. All right, so what are we doing? We're forming a ring. Let's number from the nucleophilic site to the electrophilic site. 1, 2, 3, 4, 5, 6. So we're connecting atoms 1 and 6. Clearly, we're making a 6-membered ring. That'll be the tetrahedral intermediate that I'll sketch on the right. Before I do that, well, I've drawn the ring already, but I want to number my ring atoms. I'll start at the top right, and I'll number in a clockwise direction. And now I can just add whatever is missing. maybe some highlights to help. C6 is the electrophilic site. C1 is the nucleophilic site. Bonded to C1, we have this whole ester group. Pushing these electrons back down, we make our CO double bond, CC single bond. So we have a whole ester group attached to C1. We form the tetrahedral intermediate at C6. So we break the CO pi bond. We'll end up with a single bond, negative charge on oxygen. And we have our ethoxy leaving group. Again, that's the tetrahedral intermediate, which collapses to eliminate the ethoxide ion. And this is the step that produces the product for the first time. Now, the mechanism doesn't end here. Our product is deprotonated, and during workup, it is reprotonated. The enolate is reprotonated to give the product again. But the goal of this slide is to rationalize the formation of the product, not to draw a complete mechanism. So we're skipping the last two steps. This is how this particular product, this beta ketoester, forms. I must have added a slide for examples in the past. We're going to skip that. Yes. We are going to skip that, and we're going to jump ahead. Well, not really jump ahead. To cross-Claisen condensations. So we've seen this before for aldol reactions. We can use two different carbonyl components. We can do the same for Claisen condensations, two different esters, for example. That's the first example here. What are we doing here? We're reacting ethyl acetate with ethyl benzoate. And so we're using one component that lacks alpha hydrogen so that we can direct our reaction. Ethyl acetate has an alpha position bearing 3 alpha hydrogens, so ethyl acetate can form an enolate anion and will form an enolate anion. What will that enolate anion look like? That enolate will look like this. Ethyl benzoate, on the other hand, cannot form an enolate anion. It doesn't have any alpha hydrogens, so ethyl benzoate will have to serve as the electrophile, as the electron acceptor. So the enolate formed from ethyl acetate as a carbon nucleophile will add to ethyl benzoate. So you have one clear nucleophile and one clear electrophile in your cross-Claisen condensation. So now, keeping in mind that your ester serving as the electrophile, ethyl benzoate, goes through that addition elimination process, all we need to do really is replace its leaving group with our nucleophile. So connect the alpha position of the ester that forms the enolate to the carbonyl carbon of the ester that serves as the electrophile. Know that the leaving group of the ester serving as the electrophile is eliminated. Addition elimination mechanism. And you have a fairly straightforward way of predicting your product, which is this beta ketoester. But looking ahead to the next example, you may have some questions, because one of your reactants is actually not an ester. So it turns out you can use enolate anions, or maybe more broadly, maybe you can throw in a nitronate anion. That probably also works. But you can use other enolate anions. You can use the enolate anions of esters. You can use those of aldehydes. You can use those of ketones and react them with esters. And the alpha hydrogens of aldehydes and ketones are more acidic than those of esters. So, that kind of works in our favor. So here we're using acetone. We'll turn that into our nucleophile by deprotonating. acetone is deprotonated by our base in equilibrium, of course, and that equilibrium will lie to the side of the ketone. But we'll have some enolate anions. Those will be our nucleophiles attacking the electrophilic carbonyl carbon of the ester, which goes through the addition elimination process. The leaving group, the ethoxide anion, is eliminated. And the product is still going to be a beta dicarbonyl compound. It's just not going to be a beta ketoester. That's really the traditional version of the Claisen condensation. The product here is this beta diketone. So your electrophile really has to be an ester. Your nucleophile doesn't have to strictly be the enolate of an ester. It can be an enolate formed from an aldehyde or a ketone, for example. Again, your product will still be some beta dicarbonyl compound. If you are using two esters, it'll be a beta ketoester. All right. So now, how do we recognize in a target molecule in a synthesis that that target molecule can or should be made through a Claisen or Dieckmann condensation? Thinking about the standard variant of the reaction, we need to know that the reaction makes beta ketoesters. And so that is exactly the target molecule we see here at the top. That is a beta ketoester. The beta position of the ester is a carbonyl carbon, specifically that of a ketone. So how does the Claisen condensation work? We form an enolate at the alpha position of one ester, which attacks the carbonyl carbon of another ester and thereby loses its leaving group through that addition elimination process. So the bond between the alpha and beta carbons of a beta ketoester is the bond that is formed in this Claisen condensation. That's what we need to recognize. So the ester serving as the electrophile here is an ester of propanoic acid. We'll want two of the same esters, so I'll go with an ethyl ester. There's our electrophile. And this ester would have been attacked by the ethyl ester of also propanoic acid. This is the ester that would have had to form the enolate. Form the enolate at the alpha position of one ester molecule. That enolate anion, a carbon nucleophile, attacks the carbonyl carbon of the other ester, which again goes through the addition elimination process. The leaving group is eliminated. And we have a second example here at the bottom showing the cyclic beta ketoester product. It's really the same process. The product that we see here is a beta ketoester. So the carbon-carbon bond between the alpha and beta positions of this beta ketoester is the one formed in this reaction. The alpha position is where the enolate anion was formed, and the beta position, this carbonyl carbon, is where the second ester was located in the starting material. That used to be an ester. So all we have to do is cleave the respective bond working backwards. There used to be an ester at this beta carbon right here. And that was attacked. Having trouble counting my carbon atoms. I think that's all of them. That ester was attacked by the enolate formed from the ester that's still part of your product. I think this is correct. So form an enolate here, attack there, addition elimination gets rid of this leaving group, which I don't like the way that looks. So I'll redraw this ethyl group. and that's the starting material. Now that's not very pretty, so we can unravel this. We can make this look a little bit better. This is diethyl hexane dioate 1, 2, 3, 4, 5, 6. I'm so lucky this is a 6-carbon chain. There's the starting material unraveled. Form an enolate, attack the other ester, and through the addition elimination process, we will lose this leaving group. Go ahead. Is it important that we have the ethoxy group as our leaving group here on the electrophilic site? Yes, it is, because we know that we have an ester, we have an ethyl ester on one end of the parent chain, of the carbon chain. That's this ester. And so if we had a different ester on the other side, which base would we go with? We'll want to go with ethoxide to match this ester, but if we have a different ester, say methyl ester on the other side, then that methyl ester will react with ethoxide anions. They will add and eliminate and add and eliminate. That doesn't go anywhere, but we might end up with a mixture on this side of ethyl and methyl esters. We also wouldn't be able to control what side the enolate forms on. It could form here instead. And so then we'd have the enolate of the methyl ester reacting on the other side. So our product will have some methyl esters, some ethyl esters. That's not a single major product. So both of the esters in your starting material should be the same kind in this case. And again, you may come across examples where that's not the case, especially on the worksheet, but it'll be like maybe one tert-butyl ester and one ethyl ester. And like the tert-butyl ester is too crowded for anything to really attack there. So that's not a problem. All right. Now this reaction is useful to make beta ketoesters and sometimes beta diketones, which is nice, but there is another thing that we can do here. We can use this reaction ultimately to make symmetric ketones. And so that's, I think, the last thing that we'll get into today. The formation of symmetric ketones from or using this Claisen or Dieckmann condensation through the hydrolysis and decarboxylation of beta ketoesters. And I think we'll just walk through one approach here. All right. I think this will be less colorful. I'll quit the highlighters for now, just because it's a pain, all this clicking that you have to do. All right, we'll go with ethyl propanoate, and we'll subject this to a Claisen condensation. So we need a base that matches the ester, meaning we should go with sodium ethoxide in the case of an ethyl ester, which we will use in ethanol typically. That's not too crucial to include. The base is what matters. And at the end of our reaction, an acidic aqueous workup is required, just enough to neutralize. The exposure will not be long enough to mess with the ester itself to hydrolyze any esters that are present. So the self-condensation of our ester, and I'd love to illustrate the first step here, but again, time is limited and I'm sick of clicking around, clicking the wrong thing all the time because my buttons aren't working. There is the product of your Claisen condensation, and your product has a chiral center that was just made, which means a racemic mixture will be obtained. These are your two products. Oops, these are your two product stereoisomers. I was just trying to clean this up. Okay, so you have a beta ketoester with an emphasis on ester. There's an ester. We can hydrolyze esters to turn them into carboxylic acids. How would we hydrolyze an ester? What reagents do we use to turn an ester into a carboxylic acid? This is our goal. This is what we want to make. What reagents do we need? And there's more than one correct answer. There's one that I prefer and that I'll use, but again, there's more than one correct answer. Hydrolysis, of course, requires water, but an ester plus water doesn't do anything. So what else do we need to add? Acid or base? So sodium hydroxide, hydrogen chloride. I will go with sodium hydroxide because the base-promoted hydrolysis of an ester, the saponification, is irreversible. There is no equilibrium. It's just going one way and then it's done. The acid-catalyzed hydrolysis is technically establishing an equilibrium, which, using enough water will certainly lie to the product side. I prefer the base-promoted version. You don't have to. You can use acid-catalyzed hydrolysis. And so then at the end, we'll want to acidify so that we obtain the actual carboxylic acid as opposed to the conjugate base, the carboxylate. So base-promoted hydrolysis followed by acidification to protonate the carboxylate that forms. But again, if you wanted to just use an acid catalyst, HCl, sulfuric acid plus water, you can do that. Are you familiar with the decarboxylation of carboxylic acids, especially beta-keto acids at all? So if we take this beta-keto acid and apply heat, capital Greek delta, heat, if we apply heat, a decarboxylation, a loss of carbon dioxide will occur. And what we're losing here is this carboxyl group. These beta keto esters decarboxylate readily upon heating. And this is really fun to do because these beta keto esters are typically solids. And so you can just take your solid, like your tiny little crystals, you can put them on a petri dish and put that petri dish on a hot plate. And you just crank up the heat a little bit and you can watch the carbon dioxide coming off. It's kind of like the solid is bubbling. It's hard to describe, but it looks really fun. Now, how does this work? And I don't have this in my notes, so we'll see if I can puzzle it together. Because you haven't seen this reaction before. It turns out that these beta keto acids decarboxylate easily because, let's see. Yeah, that'll work. So these beta keto acids can form a conformation that is stabilized by hydrogen bonding. Like so, right? This is a 6-membered ring conformation stabilized by hydrogen bonding between the beta keto carbonyl oxygens, well, oxygen, and the acidic proton of your carboxyl group. And this conformation is then able to undergo decarboxylation, grab this proton with your beta carbonyl group, make a CO double bond, push these electrons over to the left. This is the mechanism for that decarboxylation, the elimination of carbon dioxide, which gives this enol and CO2. And we know in a keto-enol equilibrium between any old aldehyde or ketone and its enol form, the equilibrium lies to the side of the keto form. I'm just trying to erase this O. So this enol tautomerizes to the respective ketone, and that is the product of the reaction. Okay, so beta keto acids decarboxylate readily upon heating. We can eliminate CO2, and so in the end, we will have made the symmetric ketone using the Claisen condensation and subsequent hydrolysis of the ester and decarboxylation. And that's all I've got for today. I have office hours today starting in 15 minutes. We have an hour today and an hour and a half on Monday.